In this video, I will calculate the Lagrangian of a system that has two objects, 1 and 2, when those two interact with a force that is conservative, one for which we can define a potential energy. Now, I'm gonna start by showing you this is the coordinate system I have chosen. I have the origin here, x, y. The position vector of object 1 is r1. The tip is on the object 1. The tail of the position vector is at the origin. And the same is true for object 2. The tip of the position vector of object 2 is on the object and the tail is at the origin. Now, I want to remind you, if I want to calculate the force, let's say that those are objects 1 and 2 are gravitational masses. So you can think of the Earth and the Moon, the Earth and the Sun, and so on. If I want to calculate the force that one exerts on the other one, so the gravitational force from 1 to 2, this can be calculated minus g m1 m2 divided by the position that goes from 1 to 2 squared times r hat from 1 to 2. Now I want to talk about these vectors. In introductory physics, I do go over what those are. I can remind you here. This is, so when I say r from 1 to 2, this can be calculated as r2 minus r1. What is this vector? This is, if I work on it graphically, r2 minus r1, r2 is where the tip is of this vector, and r1 is where the tail is of this vector. So if the tail is at 1 and the tip is at 2, then the vector r from 1 to 2 actually is what the term implies. It's the relative position vector of object 2 with respect to object 1. Or this is the vector that goes from 1 to 2. Okay. Now, the gravitational force that 1 exerts on 2 is dependent on this vector. The direction and the magnitude of the force depend on the magnitude of this vector, meaning how far the two objects are. But also, if I have the direction of this vector with a minus sign, meaning to the left, I know what the direction of this gravitational force is, which makes sense because 1 will be attracting 2. That's why it makes sense that the force will be pointing to the left, the opposite of this, if you look at the minus sign here. So the important quantity, this was just one example of a conservative force. If it was electrostatic, then we would have something similar. I would still need to find this vector if this was an electrostatic force. So the important quantity is not r1, it is not r2, but it is the relative position of one object with respect to the other one. Okay, it depends on how far they are, and what also matters is where it is with respect to 1. Okay, now so that was to show you that it's the relative position vector that is important. What I will remind you also here, the definition of the center of mass, it is a fraction. In the denominator, I have the sum of all masses. In this case, I have only 2. So I have m1 plus m2. And this is the sum of the product of each mass with its position vector. So it will be m1, r1, plus m2 r2, and if I had another one I would do plus m3 r3 and so on. Now I can use, let's use the big M for the sum so that I will write less, m1 r1 plus m2 r2 divided by the big M. And now we do know that the center of mass will be somewhere on this line, and the exact position really depends on the two masses. So this will be R of the center of mass. Okay, the center of mass will be here. Now, this is what I'm gonna do using this expression. From here, I'm gonna do two things. I will solve for R1, and I'm gonna have M times R of COM minus M2 R2, and then I'm dividing all of this with M1. And similarly, if I solve for R2, I will have the total mass times the position of the center of mass minus M1 R1 divided by M2. And now I will do some more work. Let's call this equation 1. Let's call this equation 2 and equation 3 so that we can keep track of all. I can solve this one, equation 1, for R2, and it will be the relative position vector from 1 to 2 plus 1. Let's call this equation 4. And I can also solve for R1, and this will be equal to R2 minus the relative position vector from 1 to 2. Let's call this equation 5. Now, I'm going to use equation 4 in equation 2. So I'm going to move on to the next step. And I'm going to replace R2 with what I have here. So it will be R from 1 to 2 minus M2 R1. And all of this will be divided by M1. Now, moving on. Okay, I'm gonna move on here because I have space. I decided I'm gonna move M1 times R1. I'm gonna move it to the left side, and then I'm gonna bring this term to the left side as well. So it's gonna be plus M2 R1. This is going to be equal times M R, the center of mass, minus M2 R from 1 to 2. Now, if you see here, I have M1 R1 plus M2 R2 R1. I can take R1 out as a common factor, and then I will have in the parentheses M1 plus M2, but this is simply the big M. And this will give me R1 is equal to the position of the center of mass minus M2 divided by big M R from 1 to 2. Okay, so again, what I did here, once I reached this step, I moved M1, this is M1, I moved this to the left side, so I had M1 R1. I also moved this term to the left side, and that became plus M2 R1. And when I add those two, I end up having big M times R1. And when I divided the right side with big M, I got rid of the big M here, and I had M2 over M on the second term. I'm gonna call this equation 6. This is an important one, so I'm gonna keep this. Now I'm gonna do something similar here. I'm gonna use equation 5 this time. So let's do m2. I'm gonna move at this point m2 to the other side. m2r2 equals the mass times the center of mass minus m1. Now for r1, I'm gonna use what I have in equation 5. And this will be the mass times the position of the center of mass minus m1 r2 plus m1, the relative position from 1 to 2. Now I will move this term to the left side. So I will have m1 r2 plus m2 r2 is equal to the big M, the position of the center of mass, and then plus m1, the relative position from 1 to 2. Now if you see here, both terms include r2, so I can take it out as a common factor. The parentheses will include m1 and m2, which is really big M. So r2 will be m times the position of the center of mass plus m1 r from 1 to 2 divided by big M, and this will end up being the position of the center of mass plus m1 over the big M, the relative position from 1 to 2. This is equation 7, and I will be keeping this because I'll be using it in the near future. So I got what I did here. I used the definition of the relative position vector from 1 to 2. I used the definition of the position vector of the center of mass, and I wrote the positions 1 and 2 as a function of the position of the center of mass and the relative position vector from 1 to 2. So let me show you something. With red, okay, and let me make a note. This is ours. This is equal to the center of mass. Okay, now with these two equations, with equation 1 and with this one, I have the position of the center of mass and the relative position vector written as a function of r1 and r2. The work that I did was really to have the opposite of that. On the left side, I have the relative position vector now and the r of the center of mass. And I have r1 and r2 on the right side. All of the work that I did here was to flip those relationships and have r1 on the left side, r2 on the left side, and the position of the center of mass and the relative position vector on the right side, both here and here. And these are the two equations 6 and 7. r1, r2, and if you see on the right side, I have r of the center of mass and the relative position vector in both of these. So I just did some work to rearrange those two equations really. Now I have r1 and r2. And what I can do is take their derivatives. Why not? Why not take the derivative of those two? So let's see, I'm going to write them again. r1. Let's see, I forgot though. Okay. Now, taking the derivative of both sides, I will have, if I use the dot notation, and just to remind you what this means, dr1 over dt is equal to r com dot minus m2, and big M are constants, so of course they do not depend on time. And I will do the same thing here. R2 dot equals R center of mass plus M1 over big M, and the time derivative of the relative position vector from 1 to 2. Now, why did I do all of this? I can remind you, if I want to find the Lagrangian of a system, I need to find the kinetic energy of the system, and I need to know the potential energy of the system. Now, for kinetic energy, since my system includes two objects, this will be the kinetic energy of one plus the kinetic energy of the other one. And here I want to remind you, I am using the classical approximation for the kinetic energy. I am assuming that the two objects are moving much slower than the speed of light. So the two kinetic energies are 1/2 m1, the speed of 1 squared, plus 1/2 m2, the speed of 2 squared. Now I'm gonna do a side note here to talk about something that I will use. When I have here, v1 is a vector, okay? It is a velocity, it is a vector, and these two lines mean that I'm taking the magnitude of that vector. Now with the square, of course, what do I have? The magnitude of the vector is the square root of vx squared plus vy squared plus vz squared. And of course, with the square, I get rid of the 2 and the square root, so I have simply the sum of the three components, each one squared. Now here is a thing, I can write this as as v dot v. So you may be familiar from introductory physics what this is. This is the dot product between two vectors. And by the definition of the dot product between two vectors, what this is equal to is the x component of the first vector times the x component of the second vector. So vx times vx plus the y component of the first vector times the y component of the second vector, so vy times vy, and the same thing for vz. But here it is, this is vx squared, this is vy squared, this is vz squared. So that is the reason that I can say the square of the magnitude of the velocity vector is simply equal to, in this case, I should have written v1 dot v1. Okay. Now I'm gonna use that property of vectors here, so I will have 1/2 m1 v1 dot product with v1 plus 1/2 m2 v2 dot v2, and I'm moving on 1/2 m1. Now v1 is this quantity, so r1 dot product with r1 dot plus 1/2 m2, and for v2 I will take the time derivative of r2 dot product with the same thing, and I'm moving on, and it's gonna get more complicated. So I have 1/2 m1. Now for r1 I'm gonna take this, so it will be r dot of the center of mass minus m2 over m, and the time derivative from 1 to 2. This is going to be dot product with the same thing, because I have r1 dot product with r1 dot. Plus 1/2 m2, and here I need to use what I have for r2 dot, and that will be the time derivative of the position of the center of mass. This is really the velocity of the center of mass, plus m1 over big M, the relative position from 1 to 2, dot product with the same thing. Okay, now here is where, I forgot the dot here and here. Here is where I will start simplifying things and start expanding things. So I have, this is equal to, all right, 1/2 m1. So I'm gonna take this and multiply it with that, and I'm gonna take this and multiply it with this. Essentially, it's the same thing as doing the expansion of a parenthesis a plus b squared. So the first term that I will have is this. This is dot product. This is dot product with the COM, the same thing. And then I have this dot product with that, so it will be minus r COM dot m2 over big M, the time derivative of the relative position vector. And then I have this dot product with that, and finally I have m2 squared divided by big M squared r dot from 1 to 2 dot product with the same quantity. Now, before I move on to do the same work here, I do want to make this look a little bit better. So that will give me 1/2 m1. Remember, it's one vector dot product with the same thing, and I can write this as the square of the magnitude, so it will be r dot COM, the magnitude. Well, let's do, just so to make things easier to understand here, since this is the time derivative of the position vector of the center of mass, this is really v of the center of mass, and that is squared. Now, here is an important property of vectors. I have r, the velocity of the center of mass with the velocity of the relative position vector, First it's v of COM, and then it's the velocity of the relative vector, and then I have it the other way around. But an important property of dot products is that A dot B is equal to B dot A. So whether you have RCOM dot product with the time derivative of the relative position vector or the other way around, it's going to give you the same result. So this is equal to minus 2 m2 over m. This is V of COM dot product with V from 1 to 2. And then I have plus m2 squared, big M squared, V from 1 to 2 magnitude squared. Now this is what the first term gave me. I'm gonna skip the steps where I work out the expansion of this, and I'm gonna tell you directly what you will get. You may be able to guess it, but you can check that. So it will be 1/2 m2, and then it will be v of the center of mass squared. Now here is a plus, so it's going to be plus 2 m1 over m v COM dot with v from 1 to 2 plus m1 squared over big M squared v from 1 to 2 magnitude squared. Alright, so after all of this work, I can see that here I have essentially 1/2 m1 2 m2 of the dot product between those two vectors. And if you take a look here at 1/2 m2 m1 with the dot product of these two vectors, this is telling me that whatever I get from this term, it's gonna cancel out with this one. So the result is 1/2 m1 plus m2 of the speed of the center of mass squared. So this will be just m and then here, let's see what that gives me. I do have 1/2. I do have from both of these terms, I will have the speed from 1 to 2 squared, and then I will have m1 times m2 squared, plus from the other term it will be m2 m1 squared, and this is divided by m2 squared. Now this is really equal to m1 m2 divided by m, because if I take m1 m2 out as a common factor, I will have m2 plus m1, and that will cancel out with the square. So the final result for the kinetic energy is 1/2 big M, the speed of the center of mass squared, plus 1/2 m1 m2 divided by big M and the speed of the relative position vector from 1 to 2 squared. Alright, and this is the kinetic energy of the system expressed using the kinetic energy of the center of mass and another term for a different kinetic energy that I will talk about. So let me show you what I started with. It's the same thing that I did before. One way is to express the kinetic energy of the system as the kinetic energy of mass 1 plus the kinetic energy of mass 2. And then doing all of this work, you can show that you can also express the kinetic energy of the system as the kinetic energy of the center of mass plus the kinetic energy plus a term that depends on the kinetic energy on the speed, on the velocity of the relative position vector from 1 to 2. Now, we call this quantity here, m1, m2 over big M, the reduced mass. So the kinetic energy of the system becomes 1/2 big M, the speed of the center of mass squared, plus 1/2 the reduced mass. So with this Greek letter mi, I refer to m1, m2 divided by big M, and this is what we call the reduced mass. Now going back to the Lagrangian, remember it is defined as Ek minus Ep. Now, the potential energy in cases like the one that I described at the beginning of this video only depends on the relative position vector from 1 to 2. Okay, it's a function of only of the relative position vector from 1 to 2. So here's the thing, this quantity depends on the center of mass, and these two depend on the relative position vector from 1 to 2. So I can call this, if you want, the Lagrangian of the center of mass, and this will be the Lagrangian of everything else relative to the center of mass. So this quantity here is the Lagrangian, the center of mass part of the Lagrangian. This is the rest of it. The important thing is that these two only depend on one quantity, the position vector from 1 to 2.